The recording is started, so Ravikant, you can take it over.
Sure, Manju. Thank you so much for a brief introduction about ourselves. Hi, everyone. Hope you are and your family members are doing good during these COVID situations. Um, Today, we are coming up with one of the important module of MuleSoft Architect course, that is choosing appropriate Mule for events. So, as an architect, while designing the applications or integration solutions, what are the things we should consider? I am going to show now. So, first thing, we need to understand the underlying MuleSoft execution engine working nature, and then how we can design different integration solutions using different design patterns. So let's go ahead one by one. Let me share my screen. Manju, can you confirm you see my screen, right?
Yes, Ravi.
Okay, great. So this all as introduced by Manju already. Um, Understanding about the thread management inside a Mule for runtime execution engine will helps us in taking care about the Mule event design process, and also take caring about the performance and choosing on top of horizontal scaling, vertical scaling, and also understanding about the thread management will helps us in scalability and saving our production environments from crash recovery. So MuleSoft execution engine as follows: observer pattern when it is handling Mule events. Coming to the observer pattern, a observable always listens events to the observer towards it, then it pushes the events to the observer. That means here we can consider the observable as publisher and observer as listener. So whenever a observable get events, it publishes to the observer. If we consider our mule flow, here the listener, which is the start point for our flow, is the observable, and the next connector to it is observer. So the logger connector always listens to the listener connector, which is observable. Whenever observable get events, it pushes to the observer. And if we see in the next level, the database connector is again observer to the logger connector, and the logger connector is observable here. Each connector is acting as a observable and observer. And if we go ahead to the flow, at the end, we have at last a request connector, which is consuming one of the REST service, and again it is responding back to the listener. Here again, the request will be the observable and listener will be the observer. Again, the listener is acting as both observable and observer. So based on this observable observer pattern, MuleSoft execution engine makes use of a scheduler component in between each observable and observer. So it is not our scheduler based connector. Internally, we have a scheduler pool which will supply threads to our flows. Suppose, assume we have 10 threads available in Mule runtime for a application. Then the flow is capable of processing 10 events at a time. Assume we are getting 10 events to the observable, then it is pushing the 10 events to the observer. Then, since there are 10 threads available, the observer can take care about execution of these 10 events. Assume now we are getting 100 events at a time. Since the observer is capable of 10 events, handling 10 events at a time because only 10 threads available, let's see how it handles the situation. So once the observable get 100 events, it pushes to the observer. Whereas the observer is capable of handling 10 events, then it will say that all threads occupied and cannot accept more. So it will process 10 events, then it will push back the 90 threads back to the observable. The concept is called as flowback pressure. which is the concept of reactive programming approach. So here in Mule 3, it used to have some memory out of errors, and also some system crashes may happen because of these unfortunate events that are coming over the events. From Mule 4 runtime execution engine, this has taken care internally. So let's see the same in demo. You may understand in better way. So for that, I have developed one process visits to a SFTP file location. Then it is reading files from input directory. Then I am just putting in the logger as got new file. Then I am doing a simple transform message as payload split by. By the way, it is reading text files which have garbage data, which look like this. So here I am transforming to split each line with /n so that it will split the entire file line by line. Then I am iterating over each file, then doing some transformation inside it as upper of some payload, then underscore, I'm keeping some underscore. Then I am adding the data to one variable called data. So I have created a variable here. So to get all this content again out of for each scope, I am appending to one of the variable. Then in the end, I am writing into a file directory called processed. Here, whatever the variable we have prepared inside for each, I am writing into that. And in the end, I am printing as finished file execution. Let me start SFTP server. I forgot to do it. Now, it is going to read files from input location. Before this, I wanted to know how many threads are available in my system. Based on that, it would be able to pick up the events, right? So about threads and types of thread we will see in coming slides, but for now, let's understand how many threads my system can capable of available. So basically, Mule 4 runtime execution engine creates the number of threads based on the processor's core size available of the system. So I have written a simple Java program to see the number of cores are available in my system. Since it executed and printed 4. So my machine has 4 cores. Based on these 4 cores, the MuleSoft execution engine calculates the threads can available to this flow. We can see that in the Endpoint Studio server, inbuilt server. So if we go to Endpoint Studio extracted location, under that we have plugins. Under that we have tooling.server. Under that Mule, under conf, we have a file called schedulerpools.conf. Let's edit with a notepad. Then here it is showing that we have the number of cores. Let me revert back. So this is how it calculates the number of minimum cores to number of equals to number of cores available in the system, and the max size of threads will be the max of 2 comma this logic. So this will provide us the number of maximum threads can available over the system. As of now, I wanted to hard code the number of minimum threads to 2 and maximum threads to 2 comma 4. So here it's supposed to be this rule here, but I changed it to 2 comma 4 because I am restricting my Mule runtime to have minimum of 2 threads and a maximum of 4 threads to show you how the flow back pressure happens in a flow. So that summarizes that I have 4 threads available, and let me run this application. Let me try to process 5 files first. Here we can notice that the pooling strategy has set to Uber. We will see about what is Uber and what is the other type we have in runtime in coming slides. But now we can see that the number of maximum threads are 4. Since I hard coded to the 4, instead of hard coding, if I could have put that calculation formula, then this could have generated the threads according to my core size, that I have 4 core size in my measure. Now let's go ahead with this, then we will see that again. Now the application has started. Since there are 4 threads available, it would be able to pick up 4 files only. What happened internally? Even though I tried to process 5 files, but the Mule event, when it has pushed, it has written 5 files and pushed it to the observer. But the observer, meanwhile, in the middle, the scheduler has supplied the number of threads as 4. Then immediately the observer had put flowback pressure on the file. Then it has neglected one event and picked up 4 files. So this is how it put a flowback pressure on the Mule events. Now we see these 4 files are processing simultaneously, and next we notice here it has completed 2 files at a time, then immediately it has picked up the other file, right? So what happened internally, once it is processing the thread simultaneously, once the thread became free, we may expect any one of the file execution has completed, then immediately it would be able to pick up the other event, other file. So this way Mule for runtime execution engine optimizes the number of events are coming towards it. It is unlike Mule 3. So with this, there are very less chances of system server crashes. And if that happens, suppose if we have capable of handling 4 threads at a time, 4 events at a time, if we are getting more than that, obviously we will see warnings in the Cloud Hub logs. If in case still the events are coming as it is, in case of REST services, the front-end user will get to know that 503 related error, and it will say that server is busy. In case of JMS related operations, the acknowledgement won't be sent to the queue back. Now, let me try to process 4 files first. I wanted to show you disadvantage because as a developer, we should have understanding about these Mule threads and how it process simultaneously. For that, let me process 4 files again. I had put this much logic. I wanted to steal some execution time to show the flowback pressure and how it picks up another file immediately when the thread becomes free. The application has deployed and it has picked up the 4 files which I loaded into the SFTP location. Then it will process the files one by one simultaneously. The 4 files execution has completed. Now let me take the starting time of the file and let me put here. I wanted to see the difference between that execution time has taken. So this is the first entry had made by the logger when it is processing the first file. And let me take the last time of the execution when it completed. Since I am processing 4 files, I am doing a divided by 4, which will give me the average time as taken for each file. So each file has taken 11 seconds of time. Let me try to load 4 more files again. Because when the first time application starts and pick up the input, sometimes it may take some longer time than usual. But if the application is already running, then the events are coming, it performs in other way. I have taken frequency as 1 minute, so it is waiting for 1 minute to run again. Let me redeploy it again, and instead of 4, let me try to process 8 files or 10 files at a time. I wanted to show the difference between the average time when it was loading the sufficient events and when it was loading or executing the events more than it expected. Now we see first 4 files has picked up, then it will process and simultaneously it will pick up the other files. And this is the start time of event. It has completed 4 files and picked up next 4 files. Yeah, we got the last file. Let's wait. The execution completes. It's a 10th file. It has completed. Now let me take the last time of the file as processed. And let me do divided by 10. So it has taken 9.4 seconds for each file. Basically, it's supposed to take longer time than initial. The initial files have supposed to be loaded in 7 to 8 seconds. What I try to show here is that when we have a heavy load, obviously it takes higher time, higher average time to process each file. But what is the why I can't able to show now, because once I run the file, then first I deploy the code, then I run the files. At the first time it processes slowly, but from the next time onwards it obviously process faster. So what I try to say here is, whenever we are getting the events more than the normal, obviously the CPU will be spiked and also the performance will be slow. So to handle that, to restrict this flow, to handle those many events, even though Mule execution engine is doing internally, still we can do that by our own hands by setting up the max concurrency. Since we wanted to handle this process 4 events at a time, we can set the max concurrency as 4, then it pick up the 4 files, then process 4 files, then again it will pick up the 4 files. During the time, the average time will be equal to process each file, even though there are more events coming towards it. Let's switch back to a next slide. So in Mule for runtime, we have 3 main threads. Apart from these 3 threads, we will also have 2 more threads. First, let's understand about these 3 threads that are CPU light, CPU intensive, blocking IO. Never a Mule flow uses same type of thread to complete flow execution. Internally, it switches the threads between these types that are CPU light, CPU intensive, blocking IO. CPU light thread are of 100% non-blocking task, whose execution time takes less than 10 milliseconds. The examples for CPU light threads are logger connector, set variable, set payload. These all connectors takes less than 10 milliseconds and which are executed by CPU light threads. And next thread we have is CPU intensive, which partially block the task whose execution time is greater than 10 milliseconds. So which partially blocks the task, not completely. The example for CPU intensive threads utilization components are data view and scripting related connectors. So we can consider transform message is executed by the CPU intensive thread. And next one we have is blocking IO thread, which is made to execute blocking related connectors, which do IO operations like database. So when these database calls are there, obviously a blocking IO thread will come, which basically blocks the execution of the thread until the IO operation is completed. Apart from Mule 3 to Mule 4, in Mule 3 we have these threads are available individual. From Mule 4.3.0, I mean before 4.3.0 until 4.2.2, we have availability of these thread schedulers separately. But from Mule 4.3.0, it has mixed to one thread pool called Uber pool. Apart from these 3, we also have 2 more threads that are related to HTTP module called as Grizzly selector threads. That are 2 types. One is shared Grizzly and one more is dedicated Grizzly. Shared Grizzly works with HTTP provider connector and dedicated Grizzly executes HTTP consumer based connector. We will usually call these as a shared Grizzly, dedicated Grizzly, because Assume we are developing 10 projects as part of a business group, and we are deploying the first project with HTTP connector, provider connector. Then only these shared Grizzly thread pools will be created. And also, whenever we deploy the HTTP provider connector based application first time, the shared Grizzly threads will be created, and those are one per runtime. Assume after that we are deploying 9 more applications with HTTP provider, then it will make use of same thread pool. It won't create separate each one for each application or each application, I mean. So it would be one per runtime, whereas the HTTP consumer uses dedicated Grizzly threads, which are one per application. So whenever we deploy an application with HTTP consumer based connectors, every time a new thread pool created to make avail of dedicated Grizzly threads. So that's why it is called as shared and dedicated. These both thread pools are of non-blocking IO threads. It uses a neo channels, which is of Java concept, basically, which whereas these two threads also works as a non-blocking threads like CPU Lite. And this is how the threads calculation will be done basically. So the CPU Lite, CPU intensive blocking IO threads created when a runtime created with a certain cores. Basically, the minimum size is the number of cores. Suppose I told you, right, my system has 4 cores. In that case, it will have 4 cores. And these thread pool will be created while runtime startup, and the maximum threads will be 2 into a number of cores. In my system, it would be 2 into 4. Therefore, it will be 8. CPU intensive also same. And coming to the blocking IO, the minimum size is the number of cores. And it also created at runtime startup, not application startup. And the maximum threads will be calculated by this formula. A number of cores plus the memory minus this value divided by this value. And on required, the increment will be happen with 1 for a application. And coming to the Grizzly shade, as discussed, when we deploy the first application with HTTP listener, then this thread pool will be created. From that time onwards, the same thread pool will be used for remaining applications for the future. And the maximum threads are a number of cores plus 1. And the increment, whenever required, will be done by 1. And Grizzly dedicated. So whenever we deploy the application with HTTP requester, it will be created for each application, and the maximum number of threads will be available for this is number of cores plus 1. So let's see the same with the example. Assume I have 4 core CPU, then the CPU Lite, CPU intensive threads will be created as a minimum 4 and a maximum 8, because we don't need these higher in number, because these will be partially blocking threads. Like the threads immediately freed up whenever the execution has done, and the threads will be immediately available for the next connectors. But coming to the blocking IO, we have more threads, because whenever some of the threads are blocking for some application and other threads should be available for other applications. For that, we have high in number for blocking IO threads. And the Grizzly threads, suppose I have 4 cores, then the maximum will be generated are 5. Let's understand how the thread switching happens in a flow. I have created a flow which utilizes all these 5 types of threads. So at first, obviously, as discussed, the listener will uses the shared Grizzly thread, then logger uses CPU Lite, database connector uses blocking IO thread, and transform message uses CPU intensive. Again, logger uses CPU Lite, and the request call consuming the other service uses dedicated Grizzly. Assume we have developed this flow and request came to the listener. The listener publishes the event to the logger, which is a observer. Now let's see how the scheduler thread pool switched between each connector. By the way, each thread pool has its own scheduler. There is no common scheduler for all the thread pools. Each thread pool maintains corresponding scheduler. So when a event comes to this listener, as we know, at first a thread comes from shared grizzly and it does the task. Then the handoff from observable to observer will be always will be done by CPU light, irrespective of the observer connector. We might saw there is a dotted line between the event source and event processor in a mule flow, right? So always this part, this middle part executed by CPU light. Now the CPU light thread will come and it executes this gap. Anyway, the next connector we have logger, so the same thread will be continued to complete the logger task. So now a thread from CPU light will come and it does the task. Now we can see there is no longer usage with the shared grizzly thread and it will come back to the thread pool. And next we have a database connector. So a thread from blocking IO will come and it does the task. There is no usage with the CPU light thread longer. It will come back to the thread pool again. And next, the transform message as discussed will be executed by CPU intensive. So the thread comes from CPU intensive and it does the task. If we see here, the CPU intensive thread has taken care the execution of the remaining complete flow. Why it happened? It's the transform message supposed to be executed by CPU intensive, then the logger connector supposed to be executed by CPU light, then this supposed to be executed by dedicated grizzly. Whereas the CPU intensive thread has taken care execution of the complete remaining flow execution, because the Mule 4 runtime engine optimizes the thread switching, because switching the threads always always switching the threads is also not a good idea. Whenever there is a chance for optimization, the Mule 4 runtime automatically do optimization of these thread switching these thread pools, because the CPU light thread is lightweight than CPU intensive, because CPU intensive is partially blocking whereas CPU light is non-blocking. That means the next two of connectors are non-blocking. That is the reason the CPU intensive continue the execution. If suppose we could have added a database connector here, then this transform message activity executed by the CPU intensive thread, then again a blocking IO thread goes here and execute the tasks. So the Mule 4 runtime optimizes a thread switching internally whenever a lower weight thread can be executed by higher weight thread. And next, even though this request call has made by CPU intensive, but internally again the response will be connected by dedicated grizzly thread, because the request connectors are meant to use dedicated grizzly thread pools. Now the blocking IO thread pool will come back to the blocking IO thread pool. Then the dedicated grizzly thread will collect the response. Then the CPU intensive thread will come back to thread pool. Then this handoff will be done to the listener using a CPU light thread, so that the user will get the response. Let's see the same in execution. So the same I have implemented here. I had a listener and start log. I am saying started flow, and then I am making a database call. I'm just fetching a data from a table, then doing some transformation. Then I am here printing as before calling API, then calling one of the service. Let me run this flow. The application has deployed. Let me make the request. Now we can see this logger and this logger has printed as CPU light and CPU intensive. We know that the logger connector obviously uses the thread pool from CPU light, the thread from CPU light, and this logger is supposed to use CPU light since the transform message used CPU intensive, so which are not much heavyweight threads, so it continued the execution to the remaining. To see all the threads utilized by each connector, let's go to log4j. And let me add debugging mode to monitor each connector execution. So just we need to put org.mule and label as debug. I need to restart the application again. It takes some more time because it is going to print the debugging logs while execution also. The application has deployed. Let me make the request. For a better visibility, let me clear it again and make the request again. Now we can notice how it has executed. At first, when event came to the listener, we discussed, right? This listener will use as Grizzly selector thread pools. The first one has used a selector thread pool. Then this logger as executed by CPU light. We can see that. Here it is saying that started flow, and this has executed by the CPU light. And next the database call, here we can see that the query that we used, this has executed by blocking thread. This is blocking IO thread. And the next one we have is transform message, and that transform message has executed by CPU intensive. And the next we had is logger. Then in the logger I am saying before calling API. So this has executed by CPU intensive, and then the next call also made by CPU intensive. Then the handoff to the listener has done by CPU light. Then user has got the response. So this way the Mule flow uses different threads. Ideally it is a single thread, but it switches the threads in between while executing the components, because there is that would be not a good idea if we execute each connector with blocking IO. Definitely optimization required to utilize the runtime memory in efficient way. So let's see more about this thread management. Coming to Mule 4.3.4 runtime, I just shown you while running an application that the type is of Uber. By default, it points to the Uber. We also have one more is dedicated. If we wanted to switch to dedicated, so the configuration file I shown just now, on the top we have the type as Uber thread pool. So we can comment these and we can go back to the dedicated and we can enable these thread pools. So because this is to customize the threads however we want. So here by default, it would be able to calculate the minimum threads and maximum threads. That's it. But it is not allowing us to customize any the other threads like CPU light, CPU intensive, and CPU intensive other threads. So here we can do optimization of those and make use of those dedicated thread pool strategy for our runtime. So let's understand a use case for a thread management optimization. Assume we have a transform message in that we have written a data view logic to call one of the Java code, which always takes or utilizes blocking IO thread, whereas the transform message intended to executed by CPU intensive. During those situations, the fix is that we can make use of Java component to call Java based code instead of using transform message, or we can change the transform message to make utilization of blocking IO thread by configuring this runtime property. But this is not recommended. It would be a costly job, so that all your transform message activities may use blocking thread. So this way we can do thread optimization. And coming to the thread pooling in transactional scopes. So if we are doing any transaction management, whenever we do transactions, all the connectors will use only a single thread that is blocking IO. In this case, these transactional scopes are not going to utilize any other thread pools. So let me show you the same in execution. This would be the last execution. I will show you quickly and I will take you through the remaining content. So here I have developed a project, simple REST service, and I have introduce the try transactional scope because here I'm making two database calls. At first, I am inserting a employee to the database, employee details. Then after that, I am inserting employee profile details to the database. Suppose if the second database call has failed due to some reason, obviously the first call should be rolled back. For that, I enabled the transaction over here. So even though we have the logger connector, a transform message activity, and logger, these also utilizes a blocking IO thread in transactional scopes. So designing the transactional scopes are required, but make sure we should be doing transaction management on required use cases. Now let me make the request. Now we can see everything has executed by blocking. Actually, it has printed only two loggers. If I enable, actually I developed this as a another application, not in the same application. So we can see even the loggers started flow, completed flow has executed by blocking IO thread. In similar way, it executes the same for remaining connectors. So while designing use cases, we should have understanding about Mule flow processing strategies. Based on that, we would able to design the use cases or integration solutions in efficient way. Coming to the Mule flow processing strategies, the first one is sequential processing. I think almost all of us aware of this. Let me walk through this PPT quickly. Assume there is task 1, task 2, task 3, and task 4 in a flow, which are depending one on each other. That means task 2 is depending on task 1, and task 3 is depending on task 2. Task 4 is depending on task 3 or some other tasks also. During the situation, we should opt for sequential processing. And assume we have task 2, task 3, task 4, whereas this task 2 is depending on task 1 and task 3 also depending on task 1 and not on task 2. During such situations, we should not opt for sequential processing. We should go for parallel processing. So here I have task 1, task 2, task 3, task 4, and task 5. In this case, this task 2, task 3, task 4 are depending on task 1, and this task 3, task 4 are not at all depending on task 2 or each other. Whereas this task 5 is depending on task 1 and task 2, task 3, task 4. During these situations, we should go for parallel processing to optimize the execution time, because as we know, we will make use of scatter gather to do a parallel event processing, so that the maximum time has taken for the task will be considered as the complete execution time for the 3 tasks have executed. And the next one we have is async processing. Assume there are task 1, task 2, task 3. Task 2 is depending on task 1, and task 3 also depending on task 1. That means that task 2, task 3 are independent in each other. The task 3 is not depending on task 2. During such situations, we can make use of async scope to execute these tasks in parallel. During these situations, 2 threads will be created and will be executed independently. But coming to the async, whenever we are dealing with async, make sure we will be having some reliability pattern in place, because assume we developed a REST service and which is supposed to do task 1, task 2, task 3. Since we hand off this task to the async scope, this will be executed asynchronously. Now the task 1, task 3 completes successfully and responds back to the front-end user. Assume the task 2 has failed, but the front-end user will be in assumption that the tasks are executed successfully, but in reality, one of the tasks has failed. During such situations, we should able to handle or implement the logic to handle those async-related tasks. So those are the 3 Mule processing strategies we have. And next, let's understand Mule event processing strategies, nothing but the design patterns. While designing a use case, what are the design patterns we can consider? In fact, these design patterns internally uses that Mule flow strategies like sequential, parallel, and async scope executions. Coming to the Mule event processing strategies, we can consider the patterns with respect to the synchronous and asynchronous. Let's understand the synchronous related design patterns. These design patterns are very useful when you are architecting a design for an use case as part of integration solution. So coming to the synchronous processing, most of us already aware of it that the source makes the request and expects the response from the target. This is called as synchronous processing. So that we can achieve by development of REST services, SOAP services as request reply pattern, and also we can make use of JMS publish consume based connectors to publish some event to the listener, and we can expect the response from the listener. And while designing the synchronous based communication, we should have idea or thinking about idempotent communication. So when we should think about this idempotent communication is that there is a use case that you are working that should take care about idempotent communication. What is idempotent communication? Assume source is making a request to the target. Then by the time the target system has processed it, while it is responding back, the source system had some network glitch. Assume client had made the request, and while he was getting the response, he had internet glitch, so he couldn't be able to see the response. The client will be in assumption that he made the request and it has not processed, or he will try to process the same request again. During such situations, the target system should be capable of handling those idempotent requests, and it should catch that and should respond back as the request has already processed successfully. So during those situations, in the second request, the response will go to the client as duplicate request. Assume consider a banking transaction. A user is making some banking transaction and the target has processed it. While responding back to the user had network glitch and he can't able to see the response. The user may try to hit the same request again with same transaction ID, but our backend should be able to handle those duplicate of requests to avoid unnecessary transaction over the banking system. Think about this if and only if required. Otherwise, our design of use case should be able to handle some upset related operation during these situations. And the next synchronous design pattern we have is content negotiation. MuleSoft inbuilt doesn't support to handle the different types on the same response payload. So for that, we basically send the content type over the header as application/JSON or XML to respond back the response in user required format. While development of experience APIs, the users might want, because we can consider some of the front end applications might be legacy applications. So those may can able to handle only XML responses. During such situations, we can expect a accept header parameter in which format they wanted to have the response type. So that is one of the design pattern with respect to the synchronous. And the next one is quick acknowledgement. Suppose a user making request to the target system, which supposed to do a life cycle of process, or which internally do some integrations, which may take longer time than the response time standards we follow for the synchronous services. Assume a REST service. During the situations, we can combinedly work with asynchronous process in the backend. So first thing what we can do is the source system makes the request, then target system do validations. If everything looks good, then it publishes to the JMS system. In fact, we can have here a backend call to save the request either into a database or any other system, which generates a unique ID and that can be maintained over the process. Once it publishes it to the JMS, then we respond back to the user as the request had made successfully. Then in the backend, the message will be subscribed by the JMS listener. Then it processed to the task 1, task 2, or task 3. It's supposed to be task 3, assume. So while positive and everything goes good, we are good because we already sent the response to the user as success. But assume while processing in the backend asynchronously, one of the tasks has failed. During the situation, we should have reliability patterns in place to handle such scenarios. So simply we can have until successful on top of this task, which at least try for 3 times with less time interval. If still that issue exists, then we can send that particular message to one of the waiting queue. Then from there we can get trigger back to the Mule event again, and we can try to process it. Those would be the reliability pattern. But still the message has not processed due to longer time unavailability of the task to internally using assume a REST service consumer. Then during that situations, and finally we can publish that to a dead letter queue. From their support team will take care that processing manually after figuring out the issue. And the next Mule event processing strategy we should think about asynchronous. So in asynchronous, we usually make use of JMS queue when we wanted to do point-to-point integration. A source system publishes message to the queue, then target system subscribes it. But when we wanted to have a broadcast related pattern like distributed pattern, one message wanted to send to different target systems. Assume I have one diagnostic center and I wanted to send patient information to the hospital. If I have integration between one diagnostic center, one hospital, then I can go for queue-based implementation. Whereas if I wanted to publish the same message to distributed environment to the multiple hospitals, during those situations, I can enable the bridge between topic and queues. And also we can make use of selectors or filters to route the particular messages to the particular queues. So we should be in a position to decide on whether we should go for queue-based implementation or topic-based implementation. And coming to the JMS, especially, mostly we consider JMS for asynchronous processing. We should be having good idea about acknowledgements to handle the reliability patterns efficiently. When we set the acknowledgement mode to auto, it acknowledges to the queue if and only if all the tasks completed the execution. That means at end of the flow, it acknowledges the message. Assume if we set the acknowledgement to loops okay, it also works same like auto, but there is a chance that it may allows duplicate messages reprocessing. And the next one we have is a manual. So whenever we set the acknowledgement type as manual, after finishing these tasks, we should take care about acknowledging manually by using acknowledge connector of JMS module. And the next one we have is immediate. Whenever we set this as immediate, so the acknowledgement will send immediately whenever it subscribes the message. But whereas if one of the tasks has failed, then definitely make sure we have reliability pattern in place to take care about the message reprocessing. And when to like most of us might have some confusion around external JMS and internal VM queues provided by MuleSoft, which one we should make use of it. So we should go for external JMS whenever we wanted to have the integrations between different applications which are not together or together in a application or intra applications. During such situations, we can have application one individual, JMS server individual, application two individual. So we can have the integrations between between these applications using external JMS server. But when we should go for VM queues, if there is a scope that we wanted to make use of VM queues, then the source and target should be in same application. We cannot distribute this to the different applications, because even though we make use of the same VM queue configurations in different applications, it cannot be communicated. If still we wanted to make use of different applications to make use of VM queue, then make those as domain projects. Then the domain projects can make use of same configuration of VM queues. Then they can able to interchange or make asynchronous communication over source and target systems. Let's understand how VM queues works in on-premise clustering. Assume we have a on-premise system with 4 nodes. Those are node 1, node 2, node 3, node 4, and Mule runtime has installed in each node. Then we are deploying a project with source and target together in one application. Then the messages should be published by source and subscribed by the target, right? During such situations, how these can utilizes or shares the messages from the VM queues. So basically, in on-prem systems, the VM queues are backed by Agile Cost VDSM queues. This is not independent application. We do not make use of any third-party application like Cloud Hub, as we have persistent queues, to make avail of VM queues as a different application. That is not possible in on-premise. So these should be available in the application itself. But when we have multiple nodes and the VM queues deployed, it generates the VM queue at least in 2 of the nodes, not in 1 node. Even it can maybe more than 2 nodes, but at least it will generate the VM queues in 2 nodes, because if 1 node is going down, then the other node will provide the VM queue to have the communication. And internally, Mule execution engine handles the both VM queues to manage the messages coming towards it, and also in similar way it distributes it. We can customize this generation of VM queues by configuring the quorum size while configuring the nodes. And how these node 3, node 4 applications will utilize. This will make use of the VM queues has generated in node 1 and node 2. And coming to the same in Cloud Hub, we have the applications as deployed into 4 workers with a horizontal scaling. Then each application has source and target. During such situations, these VM queues can make use of outside persistent queues. If we are going for transient, it will use us internally. If we make use of transient, and these executions will be individual for each worker, this cannot share the process among the workers. But when we make use of persistent queues available in Cloud Hub that uses Amazon SQS internally, so the source and target systems can make use of the VM queues externally. Let's understand how load balancing works using VM queues. Assume I have flow 1, which publishes a message, and flow 2, which consumes a message. And there are another flows like flow 3 and flow 4. I have developed this application into 3 workers with VM queues. Assume we got a event from flow 1, then assume the first worker flow 2 is busy. Then immediately it can be subscribed by the next available worker flow 2. Assume this flow 2 is also busy and had put flowback pressure on the VM queue, because this won't have sufficient thread available because already the threads are executing. During such situations, it can go to the next worker availability subscriber. So this way, a VM queues in Cloud Hub can be load balanced. Any questions? And I can go through the chart.